Log on, tune in, find out. Another good idea from Cambridge.
I'm Doliwa from the University of Warmia and Mazury. Title is the tau function of the quadrilateral lattice as Fredholm determinant within the nonlocal D-bar method.
Yes, I think everybody knows that more or less the tau function is a determinant. Yes, in different approaches you can show that it is a determinant of some for some soliton solutions or related with the Gelfand-Levitan-Marchenko equation. I will present this interpretation for the non-local D-bar dressing method, which is considered as the higher point of the inverse spectral transform method. And it will be about the quadrilateral lattice. So first part of my talk will be about the quadrilateral lattice. It will be more or less about non-commutative quadrilateral lattice. And the second part, in the second part I will be commutative, and I will show that the tau function of the quadrilateral lattice is within the subclass of solutions obtained via the non-local D-bar dressing method. It is just the Fredholm determinant. So assume that we have 4 points in two-dimensional space in general position, and in the plane of point x0, x1, and x2, draw point x12, but it must be on the plane. Yes, so if you stress that 4th point must be on the plane generated by the 3 points, then the point on the plane originating from x1, x13, and x12 is x123, but if you stress the planarity condition, then this point is unique. Basically, you have unique intersection of 3 planes, 3 generic planes in 3-dimensional space. So this is only one condition you impose, and we consider a map from n-dimensional integer lattice, n must be at least 3, to m-dimensional projective space. And somehow this projective space originally was over real numbers, but to have validity of the construction, you can take the projective space over division ring, just all axioms of the field, but not commutativity of the multiplication. Somehow the fundamentals of projective geometry tell that it is very convenient and natural to consider projective geometries over division rings. And we, of course, assume that this map satisfies that planarity condition. So every such 4 points, when now you interpret this as shifts in first direction, second, and the third direction, must be every 4 points must be coplanar. So if you start from 4 directions, for example, yes, so you add the 4th direction, so you build the last point of the cube, x1 to 3. And now if you perform all these initial steps to build 4 points, x1 to 3, 2, 3, 4, 1, 2, 3, and 1, 3, 4, then you can start building the last point of the cube with this vertex x1. And you build this point. It turns out that independently what point you start, x1, x2, 3, or 4, you arrive to the same point x1, 2, 3, 4. So via, of course, building lattice from the planarity requirement. So this is the four-dimensional consistency of this quadrilateral lattice. So the lattice is four-dimensional, in fact, multidimensionally consistent. Of course. To describe the lattice in a form of equations, let us draw on each edge of the lattice a vector, xi in direction of I lattice. It should be just non-zero vector, yes? And this point, this vector, via planarity, should be expressed as linear combination of this and this. Yes? So this is just this equation. Here is notation considered for shifts, and here's the corresponding forward difference operator. So it is just decomposition in a basis. I'm still non-commutative, and I multiply vectors from right. So I consider right vector linear spaces. Okay, to have vectors interpreted as columns, more or less. And as a compatibility condition, I obtain this nonlinear system, which can be in fact solved explicitly. The best form is to use not original Q's, but this Q hat. Yes? So starting from from some A and Q, you obtain Q shifted, and then somehow from this you obtain half of A's if you described freely half of A's here. So I call them discrete Darboux equations from historical reasons. I will explain them in a moment. But I would like to relate it a bit with the Korepanov equations picture. In fact, Korepanov considered similar linear problem by using some strings, and basic condition was that just a moment. So we have two incoming fields. Their outcomings are called psi prime and psi alpha prime, psi beta prime. And the condition was that the outgoing fields are, the result is independent of the order of interaction. Yeah, so, but everybody knows this is a kind of other language, not string, but
Ian Buxton.
What?
Ian Buxton.
Yes, but it is somehow, it is the beginning because it's in 3 dimensions. So form of that you obtain the tetrahedron property. Okay. And so about gauges, you can scale the vectors xi somehow as you want, and you obtain the same system of equations, more or less, but with different, of course, coefficients, and some of them are more convenient than other. For example, one can prove that for generic, I mean, something must be non-zero, compatible linear problems, you can gauge it to have coefficients A equal to 1. Just define this gauge function, and this system of equation is compatible because of that equation. Oops. And this is the form of the discrete Darboux equations obtained by Bogdanov and Konopelchenko. I will discuss these equations and their work further, but it is somehow still I'm still non-commutative. Okay. And why Darboux? Because the continuous version or differential version of this equation describes the conjugate nets. This is geometric object investigated by Gaston Darboux more than 100 years ago. Okay. Another gauge somehow useful is a gauge which satisfies this condition. Yes. Starting from the Darboux equations gauge, I mean that equations from this gauge, you solve the compatible system, linear system, and then the linear system can be written in this way. So right-hand side is symmetric with respect to I and j, which implies existence of the function.
Excuse me, Darboux considered continuous case,
Yes,
not discrete.
yes, not discrete.
You mean two-dimensional
No.
Laplace type transformation, no?
Yes, but Darboux considered
Suppose,
this multidimensional.
Chains and so on, Laplace transformation.
Yes, but somehow Laplace transformations were known before Darboux, but Darboux considered multidimensional submanifolds of the projective space, for which in every pair of directions you have the Laplace equation. And so you can see that there exists a function x for which this new tangent vector is a derivative. So this is just the quadrilateral lattice. So you can formulate a kind of statement that any Darboux compatible, any compatible linear problem of this type, of this type, or of this type comes from the quadrilateral lattice. Okay. Another gauge which is useful is the backward gauge. So just you, instead of expressing this pair of vectors in terms of this, you express these vectors in terms of this. Yes. So you can imagine that we can, after some gauge, we can obtain this type of equation. And now it is important to realize that these coefficients P satisfy almost the same equation like the coefficients Q here. But because we are non-commutative, it is not the same. The order is changed. Yes. And so this gauge function, which transforms the Darboux equations gauge to this backward gauge, is important because in commutative case, this is symmetric, which implies existence of a potential. It is the tau function of the multi-component KP hierarchy. But for this talk, we can say that this is a tau function of the quadrilateral lattice. Okay. Some reductions. Yes. If we are commutative, then we can consider the symmetry invariant solution or symmetric lattice for which this condition holds, or this is another expression for these coefficients. And in terms of the tau function, we can consider quartic linear equation, which apparently appeared first in a paper of Rinat Kashayev from the star triangle equation for the Ising model. And Wolfgang Schiff obtained this equation taking superpositions of the Darboux transformation for CKP hierarchy. So that's why it is natural to call this equation discrete CKP equation. Yes? And the corresponding lattice can be called or symmetric lattice or C quadrilateral lattice. Of course, there exists also B quadrilateral lattice. Yes, so this is the condition written in terms of the functions h. I will recall that functions h are given here as a gauge functions from the Darboux gauge to the quadrilateral lattice gauge. Oops.
In what sense, if any, are the previous equations included in here, the ABS equations that Jarmo was discussing?
Pardon me?
Are they included at all, the ABS equations that Jarmo mentioned?
This is a conjecture I would like to formulate.
But wait a second, ABS is in 2 space. Right?
Yes.
It's on 3 space.
Well, but if you take big N equal to 2 and M equal to 1, then it should be somehow special case.
This is what I expect, but it is a conjecture which I would risk. But okay, this requirement, this reduction, gives rise to the MIVA discrete BKP equation and the standard relation between BKP and AKP tau function is valid. Okay. So this is a half of my talk, or just a moment. So to obtain the equation in terms of the tau function, you should consider also, the so-called Laplace transforms of the quadrilateral lattice. So Lij Laplace transform, it is just you take the intersection line of this line, so in tangent I direction, with its J neighbor. Yes.
You don't associate Laplace transformation with linear operator, yes?
You can, you see, this.
Which linear operator will be this case?
Just a moment, this will be.
Second discretization
It will
of
be,
second order equation on the plane.
So
yes?
here, if you replace capital X's by this,
Yes,
it will be the second order.
it's on the plane.
Yes. This is the condition that.
Is it sum with weights along with vertices of square?
Yes.
Okay.
Yes.
It's canonical.
Yes.
Yes. Canonical Laplace.
Yes, canonical.
With quadrilateral lattice. Okay.
Yes. Yeah. Oops.
In geometric interpretation.
I don't know what's going on. Probably I was fast. Oops. Oh, okay. But to finish, so you should consider also other lattices. There is easy geometric proof that the lattice you obtain in this way is also quadrilateral. Yes, in more dimensions as well. And the tau function of this new lattice is related to the old tau function and to the coefficients Qij of the Darboux gauge. Okay. And now, the last part of my talk, it will be about the nonlocal D-bar dressing method applied to the quadrilateral lattice. So this is the non-local D-bar dress problem. Yes. So here, eta is a given rational function. R is a kernel of a integral operator with some properties which satisfy that all the calculations are valid. And chi is a solution. I omit here a lambda bar and lambda prime bar. Yes. So this is the normalization of the solution. And it turns out that the generalized Cauchy formula allows to find solutions of this nonlocal d-bar problem as solutions of the Fredholm equations of the second type. And here is the kernel of this Fredholm equation expressed in terms of the d-bar datum kernel R. So this denominator comes from the generalized Cauchy formula. So more or less people know that how you solve this Fredholm equation. You build a determinant of the matrix, yes, built out of the kernel. You define the Fredholm determinant as a series. And to solve equation, you need also a Fredholm minor, yes. And this is a kind of Kramer type solution for the linear equation. Yes. Okay. And now the idea, basic idea of the direct linearization method, that suppose you find solutions of a linear integral equation whose kernel evolves. Then you obtain also some evolution of the solution of the Fredholm equation. Yes, and you can obtain from that linear problem and other important solitary things. I'm not especially expert in history of the method, but I was told that for the first time it was applied directly without any reference to the forward, I would say, linear transform by Focas and Dablowitz. But of course, it was hidden in, not hidden. Everybody knows that to find solutions via inverse scattering method, you have to find on the way solutions of the integral equation, like Gelfand-Marchenko, Levitan-Marchenko.
I heard that, as a witness of that d-bar method is specific discovery of Ablowitz and his group. It's according to your observation.
But before the nonlocal d-bar, this was somehow elaborated as a kind of technology by Nioff, Kisper, and Kappel, and they also found discrete equations from that method. So somehow, I think that this method and the nonlocal d-bar are very connected. And Ablowitz, Baryakov, and Focas applied this nonlocal d-bar to the solutions of Kp, and Zakharov and Manakov somehow used the linear nonlocal d-bar dressing method to find generic differential nonlinear equations integrable by the inverse spectral transform. And what they found a matrix version of the differential Darboux equations. So a few years this equation was called Darboux-Manakov equations, but then Druma found this equation in the books of Darboux. So now I think it is called the Darboux equations, and the difference equations I presented are just differential analogs of it. And some condition about that kernel, we need that homogeneous equation with n eta term. Eta is here. When it is 0, it is always solvable. So it is like in linear equations that Kramer determinant, if it is not equal 0, then zero source gives 0 solution. Okay, but what is the evolution of the d-bar datum? Yes, which gives rise to the discrete Darboux equations. It is just this simple evolution. So you have this type of functions. Ni, so these functions, Ni are parameters. Lambda I plus minus are pairs of points. And somehow, if you collapse lambda plus to lambda minus, you obtain exponentials. So this is just discrete exponentials discussed in talk of Yarmo, of course. And this was applied by Bogdanov and Konopelchenko, this evolution. But this, as particular limits, contains not only the limit to the differential Darboux equations, but also to whole KP hierarchy. Okay. And this is the evolution of the d-bar datum. The corresponding evolution of the kernel of the Fredholm equation is this. Yes. And what is important then, when we shift the solution, it satisfies the same d-bar problem with the normalization. So with the source changed a bit. And now how to obtain the linear problem and solutions of the Darboux equations. Start from the solution with this type of eta, normalization. So there solutions chi I. If you have this solution, define function psi I, multiplying it by the somehow this seed evolution, and then it will satisfy n in the parameters this linear problem with these functions. The proof is standard. I mean, it is somehow, it was not directly in paper of Bogdanov and Konopelchenko, but it is not a big improvement. The proof is standard in the somehow technology of nonlocal d-bar dressing and also in the technology of the final gap solutions. You just move correct functions on one hand side, showing that this set satisfy the equation, the Fredholm equation, with the zero source. By the Fredholm alternative, it must be zero. And also, if you study final gap solutions, you do the same, but instead of Fredholm alternative, you just make use of the Riemann-Roch theorem. Okay, so this is Q. So this system is compatible. So without no effort, we know that this Q satisfies the discrete Darboux equations in the Bogdanov-Malakoff form.
It is linear, it is discrete analog of this method, yes? Do you have here also big norm, so-called big norm problem?
Of course, I always assume that
norm is small enough.
Yes, yes, that's
the big norm problem
yes,
remains.
Yes, yes, but I just assume that everything goes. Yes, so the Fredholm alternative can be applied.
Mm.
Okay, and to find the tau function, we need that gauge which goes from forward to backward gauge. It is. It can be expressed in terms of these functions, chi I. It is just a matter of simple calculations to show that this function which is obtained from chi I evaluated in point lambda I minus satisfies the same equation as G should satisfy. Yes. But of course with these Q's. And notice, this is important, that this chi I minus chi I is a solution of this linear problem. In particular, if you calculate it in lambda I minus, then this term cancels because Li in lambda I, so Li in lambda I minus is equal to 0. Yes? So for lambda I, this term cancels. And here we should put lambda I minus. Yes? Okay. And now to find evolution of the Fredholm determinant, you remember that the Fredholm determinant is that series. So you need to find evolutions of these bigger determinants. This can be done using linear algebra. On the way you obtain, you should calculate the determinant of a matrix, which is a sum of a matrix plus rank 1 matrix. Yes? This is something which is common in the business of tau function. So this is the result, the old matrix plus a term which comes from that rank 1 matrix. Notice that in that Fredholm minor we have this. If you sum up everything to the shifted Fredholm determinant, you would obtain that it satisfies this solution, it satisfies this equation. And notice that if you divide this, that this ratio satisfies the same equation like this. So this is the end of the story, because up to some trivial multipliers, you obtain the statement that up to some somehow standard factors, the same factors also are in the finite gap solutions, the tau function is equal to the Fredholm determinant of the Fredholm equation, which appears naturally in the nonlocal Debar dressing method. So these are the factors, and they are in fact the cross ratios of 4 points, lambda I plus minus, lambda j plus minus. And the same interpretation also can be given for the finite gap type solutions. So this is end of my talk. So I presented some interpretation of the tau function of the quadrilateral lattice for special type of solutions obtained by the nonlocal Debar dressing method. But I would like to recall that the geometric basis of all these things is just this simple picture, that planarity from 3 initial quadrilaters gives you 3 new quadrilaters. Okay, thank you for that.
May I ask you a following question? It is when you are doing with this technique, non-local Debar, dressing method, and so in continuum case, people compare it with some Cauchy data. Cauchy data, which class it covers. There is a so-called it's small norm, but you did not discuss in your talk just any kind of Cauchy data, or you can it cannot be also just transformed into traditional language of Cauchy data and so like some small norm problem that for all just initial values of small enough norm, everything okay, like in continuum case.
Yes, but you should have this condition of small norm.
No, you cannot do more than in continuum case. That's clear.
Yes.
Yes, but you can transform this.
I didn't do it, but I expected it can be done.
It can be done just through Cauchy data.
Yes.
Okay, that's it.
But somehow, for me, it was important to find more general interpretation of the tau function. Somehow, I am not very concerned on complex analysis.
In finite gap case, which you mentioned, there is no big known problem. That's
No.
easily solved. That's just by, say, technique of analysis on Riemann surfaces, I would say. 19th century levels solves it. But here, but in principle, so you in principle say that you can reach same level of results as done for continuum cases.
Yes.
With Cauchy problem,
Yes.
big known problem. Yes.
I expect that.
They expect it.
Any further questions?
I do have a question about very early on in your talk. You said something like everybody knows that the tau function is like a determinant.
It's a common somehow knowledge.
Well, actually, I don't know this.
Oh.
So, because if you have these bilinear equations, and then I mean, this is my question. Am I correct in thinking that they have solutions for tau which are determinants in terms of exponentials, maybe or something? But as far as I know, there are also solutions for tau which are completely different, which have nothing to do with determinants.
I only said that within this class of solutions, this is the Fredholm determinant. This is at the end of my talk. At the beginning, the tau function, okay, there are large classes of solutions for which the tau function is a determinant, or determinant of the infinite matrix, or determinant of the finite matrix, of the Fredholm determinant of the Gelfand-Levitan-Marchenko equation. But
say, if you talk about the finite matrices, are you thinking of soliton solutions?
yes,
Of course, yeah, but that's in the sense of all, in the set of all solutions, it's a very small class.
yes.
For rapidly decreasing solution, a tau function can be defined as some sort of Fredholm determinant or not?
I
don't
think
know.
people studied this. There are papers by, I would say, there is a title of Christian Pepe, Fredholm determinants as the tau function for the Kadomtsev-Petriashvili hierarchy. It was published in '88. So
But which class of solutions is described?
it was in terms of Zakharov-Shabat dressing method.
In principle, rapidly decreasing. Yes.
Yes. But somehow I am not very binded to that sentence. The tau function is determinant of everything, but people know that for many classes of solutions, the tau function is a determinant.
You have an answer to my
Well,
question?
one comment is that, you know, suppose you have a solution on KDE equation.
Yeah.
Then it is equal to dx squared of log of something.
Yeah.
That something is a tau function.
Yeah.
So if you reverse that, you have a solution, the same solution in terms of tau functions.
Yeah. So in
It
that
doesn't
sense, the
have to
tau
be a
function is a
determinant.
little bit nicer than
It should still be an entire function.
Which Q-symmetric property allow you to say that it is something like determinant? That's
No, I don't.
in this case.
So
I don't
wouldn't
know.
say
Yes.
that it's like a determinant.
So I know also a paper of Frank where he somehow writes down a kind of heuristic formula for the tau function as a determinant via some path. But this maybe Frank would
Not considered
explain
very
better.
well formed question because everything is the determinant of a 1 by 1 matrix. I mean, the entropy is not precise.
Okay.
Well, I have a purpose. I have a purpose with this remark because my feeling is that, especially, for instance, in Japan, people are focused on one very, very special, very limited interpretation of what a tau function is, and that prevents them from looking
Which
at.
interpretation?
Well,
The Jim Pomeva interpretation is pretty broad.
well, I don't know about, but it's often indeed something like this, that it's only some sort of exact solution in terms of determinants, and I claim that that sort of shuts out a lot of.
I never said that it's the only one.
Periodic band condition.
No, theta functions are finite gap, but they little bit differs.
No.
Multiplier differs well from tau function.
Well, I might even go a little bit further. I might claim that the bilinear equation in tau, to me, they're just like any other nonlinear equation. And so you can study. So, but somehow the special form means that they must be sort of considered in a special way, and then only. I mean,
Well,
that's
I'm sorry if I misled you in my previous talk, but that was if you consider solitary solutions, they will turn out to be determinate.
Yes.
Yes. But of course, we can consider Cauchy problem. Of course, it's the same equation because it's a evolution equation. You can go through all the motions and the Sato theory. That the Jim Pomeva constructions, they are much more general than solitary.
Okay, but I have a
It is
definition.
indeed formal solution.
Yes.
Practically all formal.
Right, general vertex operators.
So I
But
have.
if you are dealing with Riemann surfaces and conformal field theory, there are so-called representation theory, semi-infinite product, and in this approach looks like there is more similarity to determinants. That's if compared, yes, infinite dimensional. That's if compared with solitary theory with conformal field theory.
But
Tau function appears as some really based in some semi-infinite external product. So that's how it appears in representations of Virasoro algebra, this Fagan-Fuchs. Also, that's there is more similarity with determinants in that case.
But here is definition of the tau function without any relation to determinants. It tells that in many particular cases, is this just determinant?
So how about ABS? Come back to that.
So
That's somehow included.
this I believe, because I remember that in Tasso's talk, he presented some reductions of this equation, which lead to one equation of the ABS list. Was it true or not? I do not remember.
Let's
That doesn't fit with what Yama was saying in that
Yes.
all the ABS list corresponds to not BKP but AKP, standard KP.
Yeah.
Yes.
Seems to be okay.
So somehow
What
this
is
equation.
AKP? Is it
Well,
standard
discretization
procedure.
of KP?
It's fully discrete KP equation, yeah.
Is not it Hirota?
So this is the
Hirota
first.
equation.
This equation it is just
totally
AKP.
symmetric in all three discrete values. Okay.
So this is not symmetric, but it can be put in a symmetric form.
Okay, any further questions?
Four terms. B.
Can you show the BKP equation?
BKP.
See, that has four terms there.
It's more
So
symmetric.
the term on the left-hand side is the X.
Yeah. But I mean, here it sort of looks a bit asymmetric because of the. But well, it depends on.
No,
if you
the
look at it from the
right-hand
point
side
of
is
view of the
symmetric.
cube, these are all four diagonals of the cube, whereas otherwise you just have three, which is, I would say, less symmetric.
Okay, but if you would like to write down this equation in terms of the tau function, it will be octolinear equation, I would say.
That's again. I mean, so what's so sacred about this tau function?
Is a kind of solution. integrable linear discrete equations. But it is a kind of one field which encompasses how many different somehow equations also.
So maybe this discussion can go on afterwards. So let's thank health people
Okay.
once again.